In this series, I'm going to be going over the MIT OpenCourseWare course on electricity and magnetism. For reference, I'm a high school student and this is college physics, so we'll see how this goes. I want to create a unique dynamic where I'm both the student and the teacher. This is episode 1. What does an apple, a phone, and a table all have in common? Well, they're all interacting with the force of electricity, and pretty much everything is. The interactions happening in your body, the earth, the sun, pretty much everything that has mass has to interact with electricity. Now, to understand electricity, we have to look inside the atom. So in chemistry class, we learned that the atom is broken up into the nucleus and the electrons that orbit around it in a cloud. Now, what's important for this course is that the protons are positively charged and the electrons are negatively charged. Something interesting to note is that this picture is not to scale. The electrons are much smaller than the protons and neutrons, and the space in between them is actually much, much bigger. Now, a really big concept that was talked about in the first lecture was this idea that opposite forces attract and like forces repel. That is, a positive and a negative attract, and then a positive and a positive repel, a negative and a negative repel. So if we go back to the atom, we see that the proton and the electron will attract each other because they're opposite forces. And the proton and the proton will repulse each other because they're the same charge, and the electron will also do the same. The next thing I want to talk about is this idea of induction. And induction is where charged objects rearrange charges of another object without touching it. Now, how can this happen? Well, if you take a glass rod and rub it with silk, at least that's what they did in the lecture, and the professor explained this because he said friction creates charge. Why this is, I'm not sure, but I'm sure we'll get into that later. So the main thing right now is that the glass rod is positively charged. And then we take a balloon that is just neutral because it's just there. We move this positive rod closer to the balloon. Now, what do you think is going to happen? Well, based on the principle we learned earlier that opposite charges attract each other, we see that the negative goes towards the positive, and we get this concept called polarization, or we can say that this balloon has been polarized because this side of the balloon is slightly more negative and this side is slightly more positive. And because these are opposite forces, there's going to be a force between them, and the balloon is going to end up going towards the glass rod and it's going to try to follow it. Now, I said that this side becomes negative, but how does that happen? Well, in metals, they are called conductors. So conductors and metals, you can think of them as the same. Now, what a conductor does and why it's important is that the electrons within them move freely. And now if we remember from the structure of the atom, electrons are the negatively charged particles. So in this balloon, all the electrons have kind of moved, kind of like a liquid, almost going over to this side because they can move freely within the object. Now, what if the balloon is not made of a metal and it's something like rubber, which is very common? Well, that would be a non-conductor. Yet this effect will still happen. And for that, let's look at the atom again. Now, I've said that a non-conductor, the electron cannot escape the nucleus, but they can still rearrange themselves within this kind of boundary, if you will. So the electrons will go over to the side that has the positive. Let's just pretend the positive is over here. The electrons will kind of go to the left side, and the nucleus, which is positively charged, will go over to the right. So we end up still getting that all the electrons kind of shift over this way, making this side a little bit more negatively charged and this side a little bit more positive. Now let's talk about Coulomb's law. This is really taking everything we learned and making it into mathematical representation. So we already said that there will be a force of attraction or repulsion with two objects that have a charge. Now, the force of both of these objects on each other is the same, and that's because of Newton's third law. And then that is going to be equal to K, which is Coulomb's constant. This is just a number. Don't really need to care much about that. And then the charge of the first object multiplied the charge of the second object. And now this is all divided by the radius squared, and the radius is just the distance between these two objects. Now let's look at an example to really lock in this idea. So let's pretend that we have our proton and electron, and remember, the proton is positively charged, the electron is negatively charged. Here is the Coulomb's law for reference, and like I said, Coulomb's constant is just a number, so there it is. Now the charge of the proton and the electron are the exact same, except they're opposite. So this is the number that is there charged, and the magnitude is equal. However, the sign is different. So when you make the calculation, it does matter. Now the radius, I just picked a random radius, which is pretty close to how far apart the proton and electron would be inside the actual atom. Now you plug the numbers, you chug, and this is what you get for the force. So using Coulomb's law and an example of a proton and electron, we've just calculated the force of attraction between them. And that's pretty cool. Now what happens if there's 3 charges? Now we know how to calculate the force between 2 charges. So for example, if we're taking a look at this electron and this top proton, we could find the force of attraction. And we could do the same for this proton and this electron. And since they're opposite, we'd find this force of attraction. So there'd be a force going this way and a force going this way. And since we've kind of found the components, what we can actually do for the net force is we can just add them together. Why this works, we don't really know, but it follows all the experiments, so we kind of assume that it is true, and it makes the math a lot easier. Now I want to look at Newton's law of gravitation. If you're not familiar with the law, here it is. Now, side by side, we can see that these two laws are very, very similar. You have the masses and the charges that are almost interchangeable, m1 times m2, q1 times q2. You see the constant g here, constant k here. So we see that these ratios are just multiplied by some number, right? So the force is proportional to these ratios. And then finally, we see the distance. That is both there, and it's both the distance squared. Now, it could have been anything else. Like, even the smallest change, such as the distance, could have been cubed in Coulomb's law or in the gravitational law. But these two forces of nature act so similarly, and we can see the proof right here in the formulas that model their force. Now, why this is, well, nobody really knows. But it has to do with just the beautiful underlines of physics and our natural world, and how kind of beautiful and simple everything really is. So just something to take in mind and be inspired by. Thank you for watching this video. I hope you learned something. I definitely did. And in the comment section down below, please tell me what I can improve on, what other things you want to see, other topics you want to see. I hope to continue this electricity and magnetism unit. Episode 2 will be on electric fields, so be looking out for that. Thank you.